Hello, everyone. Welcome to the webinar. We will begin in a couple of minutes. Please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 people in the room, please enter the number of attendees present in the questions box. Hello, everyone. Welcome to EPA's 17th Annual Drinking Water Workshop. We are glad you could be here virtually with us today for webinar session 2A on Monitoring and Distribution Part 1, Disinfectants and Disinfection Byproducts. If you have not done so already, please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 people in the room, please enter the number of attendees present in the questions box. Now, let's hear from Alan Roberson, who will introduce our first speaker and help moderate the webinar.
Thank you. Again, my name is Alan Roberson. I'm Executive Director of the Association of State Drinking Water Administrators, one of the partners with EPA on this workshop. We have a great panel coming up, a nice representation of one student, one state representative, one EPA representative. So with that, I'd like to introduce our first speaker, Nelson Daluz. Nelson is a PhD student in civil engineering at the University of Massachusetts at Amherst. So take it away, Nelson.
Thanks, Alan. Just gonna share my webcam as well while we're here. All right, welcome everyone. Thanks for coming to my presentation today. I'll be presenting on some of my research on evaluating impacts of sampling design on the outcomes of drinking water quality monitoring programs. So the motivation behind this work: water quality monitoring is required by the Total Coliform Rule, as most of us are aware. And the Total Coliform Rule's purpose is to improve public health protection by reducing fecal pathogens to minimal levels through control of total coliform bacteria. And the Total Coliform Rule says that sampling locations should be representative of water quality throughout a distribution system, but representative isn't further defined. Publicly available guidance for sampling location selection seems limited, so this makes choosing representative locations difficult for some suppliers. I want to show that how we define representative and when we sample can affect how accurately we're able to represent distribution systems in different scenarios, because how well we do this is an indicator, or it can be an indicator of how well we're meeting the goal of protecting human health. This is an overview of the methods I use for this project. I'm not going to read everything on this slide right now because I'll be going into it in the other ones, but the key parts of this are tying sampling program designs along with water quality models and then evaluating systems based on those designs and models. Sampling program design. So for these different designs, I use different definitions of representative, and these definitions of representative mostly focus on location. And I use GIS to implement these location methods. Other aspects of these programs beyond location include the location selection method, the sample collection time, and the number of samples collected. The first aspect that I'll go into more detail on is the location cases. So this is how do we define representative in terms of location. I use 6 examples here. It's not an exhaustive list, but the location cases I use fall into 2 main categories, representing the whole system and then representing worst quality in the system. For the whole system cases, we have a fully random samples location selection, a geographical grid layout, and then a balanced allocation stratification. Then for worst quality, we look at the furthest 20% of locations, locations that might be below the target at least 50% of the time, and then extremities and dead ends in our system. To give a better visual idea of what I'm talking about with these location cases, here I show the examples of the GeoGrid case, or the geographical grid overlaying the network. So in that case, you can see there's a grid overlaying the network, and then sample locations get selected from each of the individual grid cells. And then a balanced allocation stratification, where in each ring moving out from the source, an approximately equal number of sampling locations get selected. To look at our other cases and visualize those as well, for the all or the random location selection, you see that every single spot on the network is available for selection. And then for our worst quality cases, the furthest 20% of locations, those are the only ones available. For the below 50, that's a case where this is based on simulation, but the idea of it is, where might a utility expect that they're going to have poor water quality based on past conditions? And then extremities and dead ends are included as well for the dead ends case. The next aspect, beyond just the location cases themselves, is the location selection method. So these fall into 2 main categories. The first being varying locations, meaning that every week there's a potential different pool of locations that can be selected. And then the opposite side of that is using constant or fixed locations. So the 2 that I'll mainly focus on are what I call a locked and unlocked configuration, where in the locked case, we're saying, for example, we sample at site A in our system on Monday every week. And then in the unlocked scenario, we're talking about a situation where we sample at site A at least once a week. It could be on Monday or Wednesday or really any day. And then in addition to that, there's a double and triple configuration, where we're not totally doing a complete random selection, but we do have a pool of locations that we can use. So that covers most of the aspects around location. The next aspect is the timing of the sampling program. So I used 3 examples here. The first is 24 hours or any hour of the day. So that's saying a sample could be taken at 7 a.m., it could be taken at 8 p.m., midnight, anytime. And then there's 2 restricted timing scenarios, 7 a.m. to 12 p.m. and 6 a.m. to 4 p.m. And the reasoning behind having these restricted timing scenarios is to see the effects of potentially a water supply or utility. They only have people go collect samples during normal working hours when most of the activity at their treatment plant might be going on, for example. And then results relating to timing, we look at on both weekly and daily timescales. Sampling frequency. So most people know that the total coliform rule, it requires suppliers to take a certain number of monthly samples based on a population served. And that's a minimum number of samples, of course. But what we did is we end up using, I'll get into it in the next slides, but I used 2 different networks in this example. And what we do is we take the population that's served by that system, associate that with the minimum number of monthly required samples from the total coliform rule. And then I am using an evaluation period of a week. So since, for example, one of these systems, 150 samples is the monthly requirement, we divide that by 4 weeks in a month approximately to get about 5 samples that would be needed per week in order to meet compliance with the number of samples required. For the example networks, so as I had mentioned on the previous slide, I used 2 different pipe networks in this study. And the idea behind using 2 different networks is to see the differences between systems of different sizes. One is much larger than the other in this case. And then see what happens when we apply sampling programs to these networks. And even though I've been mostly referring to the total coliform rule, there is typically a requirement that disinfectant residual has to get measured along with any total coliform measurements. So I use chlorine residual as a proxy indicator for bacteriological quality for these 2 networks that I'm working with. And what I do using the water quality model results for chlorine or free chlorine, I compare the effectiveness of the sampling programs by quantifying what I'll refer to throughout this presentation as the percentage of samples less than the target concentration, or PLT value, which I'll describe in more detail in the next few slides. These are my 2 example networks. The first one on the left side of your screen is from a project called Battle of the Water Sensor Networks, which has an associated paper published with it in 2008. So that system serves about 250,000 people, and it has a number of tanks and pumping stations throughout. And then on the right side is the other network, which is much smaller for a Midwestern small city that serves approximately 20,000 customers. It's got a number of pressure zones involved with it, And that is from a paper, Wong et al. 2017. For both of these networks, I used water quality models or developed water quality models. And the way that I did that was using EPA-NET, which many of you may have learned about or be familiar with from the training session yesterday afternoon, East Coast time. That EPA-NET is a hydraulic and water quality modeling software freely available from EPA. So I used EPA-NET 2, and I used it to model free chlorine concentration in both of these networks. For both networks, I had an average free chlorine residual of 1 milligram per liter, leaving the treatment plant, or the source in this case, and I use a 1-week simulation. As a bit of an example of what that looks like, the figure on this slide demonstrates chlorine concentrations throughout the network at just a snapshot in time for the BWSN Battled Water Sensor Network for day 4 in the middle of the day. You can see in the red, those are the points that are below 0.2 milligrams per liter. So my sampling metrics and statistical analysis. So as I've mentioned a couple of times now, the main metric that I'm looking at is the percentage of samples less than a target concentration. The target concentration that I used is 0.2 milligrams per liter of free chlorine. The reason for using that 0.2 milligram per liter value is that it's cited in a number of documents and literature as being a minimum amount of free chlorine that you would like to measure at a point in a given system to be able to say that you won't have bacteriological issues. That PLT value gets compared to what I'll call a true PLT or PLT actual value, which is the true percentage of possible samples that could be taken across any point in the network that's being considered, across any time step that could be considered, that is less than the target concentration. So for example, for the BWSN Battle of the Water Sensor Network, the PLT actual, the denominator here, the bottom half of the equation is saying, looking across every single point in the network, across every time step that we have measurable, we use hourly time steps. And then on the top is any value that was below 0.2 milligrams per liter across that. So what we get from this is a value of 10.6% approximately, to say that 10.6% of locations across a given week-long period in this network are going to have a free chlorine concentration less than 0.2 milligrams per liter. I then use a number of statistical tests, and the purpose of these statistical tests is to see differences between different timings, differences between number of samples that are collected, and then ultimately just comparing what we actually measure for the PLT, percentage of samples less than the target, that we observe from the sampling program results, compared to what the true PLT condition in the network is. Now I'm going to finally get into some results. So first we'll go through the BWSN Battle of the Water Sensor Network, Network 2. And in the next slides, I'm going to ask some questions and then answer them. So the first question that I asked is, does the number of samples collected in a week change the results from the sampling program significantly? So again, keep in mind that we're talking about free chlorine is our water quality parameter of interest here. And by looking at this figure, this box plot, the vertical black line that cuts through the boxes, that represents the true PLT or PLT actual value. And then you can see that we have our different timings and then different numbers of samples. So I compared 38 samples for this network, which would be the scaled down minimum number of weekly samples that should be taken, and then a scaled up version of that at 56 to say, you know, what if we took just a few more samples? What would happen? Would we see a different result? And the answer to that question is most of the time, not particularly. So because of that, moving forward, I'm going to be using the sampling frequency of 38. The next question I asked is, how well do the sampling programs perform over the course of a week? So to mention from earlier again, our whole system location cases are all the geogrid and the balanced stratification. And again, you can see the vertical lines that cut through are the PLT actual or true PLT values. And then from the box plot results, you can see for the geogrid and the balanced stratification that the median value, which is the thick part in the middle of the and the inside of the box, that we're getting an overestimation of the percentage of samples that are less than the target concentration. However, when we look at the worst quality cases, these do a bit better in terms of accurately representing the percentage of samples less than the target concentration. So that's our furthest 20% of locations, below the target 50% of the time locations, and our dead ends in the network. So that's over the course of a week, but sometimes we might be more interested in what happens over the course of a day. And the results were pretty similar to what we saw over the course of a week, in that on average, the true PLT conditions can be accurately represented, except for when we're using that grid overlaying the system, the geogrid, or the balanced stratification, where we take an approximately equal number of samples in rings coming out from our source. And it's worth noting that I did focus on single source systems in this study. And the other conclusion that we can make from this is that timing of when samples collected, whether it was any 24-hour of the day or within the restricted timing of 7 a.m. to 12 p.m. or 6 a.m. to 4 p.m., it didn't make a big difference in the results that were observed. But we also all know that our systems aren't static. They don't stay the same all the time. So I ended up modeling an operational change. It's a bit of an extreme case perhaps, but it demonstrates the point in that the scenario that I used, I have the chlorine leaving the source set to 0 for 4 hours starting at noon on the third day of the simulation. And the thought process behind this is maybe there's some sort of malfunction in equipment at the treatment plant or facility that could cause some sort of problem. So that's a pretty significant operational change. And I'm demonstrating results for the fully random or all location case here. This kind of applies for all the other scenarios, even those not shown here. But somewhat unsurprisingly, timing does become more important where it wasn't previously. If we look at day 3 here, you can see it's in this box. What we would want to see is the black dot to line up with the top of each of those bars pretty closely. And you can see that it somewhat does that for the all times or 24-hour, any 24-hour of the day scenario. But then when we have a restricted timing scenario, then we see that it completely misses this event. So it's something important to consider. Next, we look at what happens when we have fixed or constant sampling locations. So again, I have these locked and unlocked scenarios. In the locked, we're saying we sample at site A on Monday every week. For unlocked, we're sampling at site A at least once a week. And then we also look at what happens if we double or triple the pool of potential sites. And pretty much across all of these are all for the all or fully random location selection case. What we see is that when we're trying to represent this percentage of samples less than the target concentration, we're not able to do that very effectively if we have fixed locations. This shows the locked scenario for other things, for the other location cases, the grid, the furthest 20%, et cetera. And we see the constant sample location selection again, generally not able to accurately represent those true PLT conditions. Then we also did a quick comparison between what happened, like what if we compare constant locations with varying locations. And as you can see, there's a lot of red on this table, and the conclusion from that is that the varying location selection method, which typically did a lot better, these constant location cases do not perform as well. For our Midwestern small city, our results for that, again, we ask ourselves, does the number of samples collected change the results from the sampling program? So for here, the number of samples that we're working with is our minimum required is 5, and then we compare that to a value of 10. And again, similar to the BWSN, we didn't see much of a difference for most cases. So moving forward, I'm going to be using 5 samples for the rest of this section. So what do we see? We see again that for the whole system, the all case does a lot better than the GeoGrid and the balanced stratification. But then for worse quality, we see the dead end still performs well, but the FAR 20 and below 50 did not perform as well as they previously did. Then, somewhat unsurprisingly, if we look at what happens over the course of a day, when you're only taking, let's say, 1 sample per day, you're not going to be able to accurately represent a system-wide condition with only 1 sample per day. You're either going to get a value of 0% or 100%. So we know that the actual true condition is somewhere in between that. So we have to keep in mind of how we're interpreting our results if we're using this metric. Again, looking at constant sampling locations, we see that using the constant or fixed sampling locations, that it wasn't likely to represent the true conditions in the network very well. There was only 1 out of most of these cases that was able to accurately represent the condition. Then, so I used 2 networks. I think it's important to compare the 2 of them to each other and pull some information from that. So the first bit that we can pull from it is that the dead ends programs tended to be best at approximating worst quality in the system. We also saw that the geographical grid or the grid layout for choosing locations was not able to accurately approximate the true percentage of samples less than the target. And we also saw that the timing of sample collection was slightly more important for the Midwestern small city network. So this goes to show that hydraulics are an important thing to consider, and the way that your system operates and how big it is can affect how important timing is going to be for you. So our overall conclusions from this. On sampling locations, we can conclude that achieving accurate estimates of worst quality conditions was more likely than accurate estimates of system-wide conditions. For timing, the importance depends on the network, but it's really important to consider operational changes that are happening in your system. On the number of samples, that it's not appropriate, most likely, to make system-wide conclusions when you have a very few number of samples, let's say 1 or 2. And then on using fixed or constant sampling locations, that using these can make it difficult to accurately represent conditions across your network. The implications of this. So first off is, if we're trying to get full geographic coverage of the network, for example, using the balanced stratification or the geographical grid, that the sampling program results can make you think that there's a lower system-wide free chlorine residual than there really is. And this has some management implications. You might be dosing more chlorine than you need to, and time, money, resources, trade-offs need to be considered with that. That you need to think about your evaluation period. Is it daily, weekly, or monthly? And if those are your different periods over which you're evaluating the results of your sampling program, how do operational changes and demand pattern changes affect those things? We also see that the total coliform rule required number of samples, that it might be fine for total coliform, but for other water quality parameters such as free chlorine, maybe a different number of samples might be more appropriate. And then that it's really important to consider how you're going to evaluate your results if you use fixed sampling locations in your network. For future work related to this, I'd like to link some field sampling with water quality simulation to better quantify real world water quality conditions. And then, as I mentioned with the operational changes, but you also want to consider things like seasonality, changes in water demand. And we also might want to consider what happens if we use a different disinfectant, such as chloramines. I'd like to acknowledge a few people. First, my advisor, Dr. Emily Kumpel, then Dr. Vanessa Spite for providing the Midwestern Small City Network, Dr. John Tobiasen for his help with coordinating through using EPA-NET, Dr. Colin Gleason for his feedback on use of GIS, the EPA Drinking Water Workshop organizers and the Cadmus Group for all the hard work that went into putting this awesome event together. And with that, I want to thank you all for listening in on my talk. If you are interested in reading the paper associated with this work, it's published in Water Research. You can scan this QR code on the slide, and that'll give you free access to the article until September 19th. So with that, once again, I'd like to say thanks to you all and send it back to Alan.
Thanks, Nelson. That was a great paper, and we'll answer some questions in the Q&A panel. Feel free to put those in there, and I'll do more as the questions come in there. So again, put all your questions in the question panel, and we'll answer them after the next two speakers. We've also got handouts, the compiled slides, files for everybody, as well as an agenda for the entire workshop. And with that, I'll introduce our next speaker, Candy Thompson, a project engineer at Oklahoma DEQ, who's going to talk about some of the innovative programs they've been doing in the state of Oklahoma, coincidentally where I was born and raised, to address DBP. So take it away, Candy.
Hello, everyone. Thank you for joining me today. We had some technical difficulties earlier, so I'm going to try this and hope that it is working out for me. It appears that it is working. I think can someone confirm if they can see my screen?
Yes, we can see your screen.
Wonderful. Thank you very much. That's good news.
Oh, now we're seeing a white
Oh, no.
box.
Well, that's what I was worried about.
Okay. I will throw up your slides and just tell me when to advance.
Okay, thank you. Are you ready for me to?
Yes, sharing my screen now.
Okay. Okay, thank you very much. Well, as Alan said, my name is Candy Thompson, and I'm a project engineer with the Drinking Water State Revolving Fund at the Oklahoma Department of Environmental Quality. And today I'm going to be presenting on Oklahoma DBP Compliance Assistance. And that's a picture of me at one of my Oklahoma City projects inside a 120-inch Hobos pipe that they're working to get installed. Go ahead and advance. An overview of my presentation includes disinfection byproducts, DBPs in Oklahoma. Then I'll talk about the area-wide optimization program known as AWOP. Then the Drinking Water State Revolving Fund, DWSRF subsidy, and then I'll conclude with some lessons learned. Go ahead, please. Disinfection byproducts, DBPs in Oklahoma. Oklahoma has approximately 1,360 total public water supplies, and 890 of these are required to monitor under the DBP rules. And 108 of those 890 are currently under a consent order for DBPs. Oklahoma has approximately 78% of their health-based violations related to DBPs. And as many of you know, EPA's goal is to reduce health-based violations by 25% by 2022, which is less than a year and a half away. It goes by so quickly. So we have been trying, Oklahoma's been working very hard to reduce our health-based violations, specifically all those DBP violations, through AWOP and the DWSRF subsidy. Next slide, please. Now, this map, it gets thrown up there quite a bit when talking about DBPs. I know a lot of people, my coworkers and I from Oklahoma, kind of cringe when we see this. It does represent the relative density of systems with DBP health-based violations. And if you're not familiar with Oklahoma, the western half of the state is primarily groundwater, and the eastern half is mostly surface water. So that's where we have our problems. And we're hoping through the AWOP program and the DWSRF subsidy, we can change the colors on this map in the near future. Next slide, please. So let's talk about the area-wide optimization program, AWOP. If you're not familiar with AWOP, it's a multi-state effort in which states work together to develop and implement individual state programs to optimize things like turbidity, of course DBPs, iron and manganese, chloramines, chlorine, storage tank detention times, harmful algal blooms, HABs, and many more. The entire program is mostly not enforcement. There's a small piece that I'll talk about in a couple minutes, but overall it's not an enforcement program. AWOP sets goals for going beyond regulations and requirements, and one of the key elements is transferring knowledge to the water operators. Operators are operating their water systems every day. They're producing the water, sending it in distribution, sampling it, and providing safe drinking water to everyone. So if we don't have their buy-in for optimization, AWOP will not be a successful program. In addition, AWOP helps water systems operate as effectively as possible, and it focuses on fine-tuning what a water system already has in place and not spending money for additional infrastructure. The reality is additional infrastructure may be needed, but if you optimize first, you can focus on the best place to put that funding. Next slide, please. Okay, AWAP in Oklahoma. Back in April of '99, EPA came to Oklahoma to do their multi-state pilot kickoff. And Oklahoma has been a part of AWAP ever since, so over 21 years. Region 6 has always been strong in AWAP, and we're currently attending quarterly meetings with not only Region 6 states, but also Region 7. Several years ago, Region 7 did not have a program, and Iowa asked if they could join Region 6's program, and so we welcomed them, as well as Missouri and Kansas, and now we have a joint program, and we've recently welcomed Wisconsin as well as Minnesota. So it's such a privilege to work with all these states and the EPA regions and learn so much from them regarding optimization. The next 6 items I'm going to talk about in more detail in subsequent slides. They include Oklahoma's DBP optimization goals, some of the special equipment we have to help with DBPs in our water systems, comprehensive performance evaluations known as CPEs, performance-based training, PBTs, AWAP awards, AWAPA, and our DBP pilot project. Next slide, please. Oklahoma adopted the national DBP optimization goals, and you can see on the slide here for total trihalomethanes, TTHMs, for the short-term goals at the individual sites, and short-term is over 4 quarters. We'd like to see less than 80 micrograms per liter, and then the long-term goals over 8 quarters is less than 60. And then for the 5 halioacetic acids, HAA5s, the short term is less than 60 and the long term is less than 40 micrograms per liter. The regulations require a 1 TOC, total organic carbon removal ratio, but optimization goes beyond that and wants an additional 10% removal, so we ask for a 1.1 removal ratio for TOC to meet those optimized goals. Next slide, please. Oklahoma is lucky enough to have some special DBP equipment that we can go out and use in our systems to help understand how DBPs are formed and help develop solutions with the water systems. The THM plus method allows us to go out and get samples from each water system and then run those samples at a fraction of the cost compared to sending samples to a lab. However, the samples measure more than just THMs. They also measure HAA5s. So it doesn't give you a regulatory value to compare, but it does give you a baseline to see if your THMs are increasing or decreasing or staying the same in the distribution system. We're also lucky enough to have a portable total organic carbon TOC analyzer. And this becomes critical at surface water plants when we try to look at the amount of organics removed from each treatment process. So we can take that analyzer out to the plants and grab samples and tell them on site what their organics are through each process. And we can also grab samples and bring them back to our office and run them too, which is sometimes more efficient. Now these analyzers are $20,000 and up. So we've learned that it is critical to have a maintenance contract and make sure that the units are maintained regularly to give you accurate data. And the final thing is the hydrant samplers. Several years ago, Oklahoma hosted one of those quarterly AWAP meetings, and the National Optimization Leadership Team had developed a workshop to use these hydrant samplers, and they provided a list of parts for us to construct our own. And I do have that list if anyone's interested. I can provide that. And Oklahoma constructed 2 of those. And what they do is they allow you to attach to a fire hydrant and collect a sample at a known flow rate. And it makes it a lot easier to get samples from a hydrant, but also if you're trying to calculate a specific flush time and get water from a particular area in the distribution system, you know the flow rate that's going to be coming out of that hydrant, and it's helpful in doing that as well. Next slide, please. Comprehensive performance evaluations, CPEs. This is one of the foundations of AWAP. New states that are joining AWAP, a lot of times they start with CPEs, and they identify limiting factors in 3 major areas, which include design, operation and maintenance, and administration. And when we have new staff join the AWOP program and they go to a CPE, a lot of times we hear that it is the best training that they've ever had because they get immersed in the water system for a whole week and they get to do a lot of hands-on items and is excellent training. As you can see here, it says you spend a week at the public water supply. That's the main part of the CPE, but you do collect data beforehand and even do a pre-CPE visit, and there's a report to write afterwards. But during the week you're at the plant, for Oklahoma, we spend the first day with an entrance meeting and a plant tour. And we spend the next 3 days doing things like interviews and special studies and various evaluations at the plant. And then we do an exit meeting that final day. Some of the special studies we look at include chemical verifications, data integrity for turbidimeters and chlorine analyzers. And we've also added in the administration portion a water loss audit as a special study. Now, CPEs are traditionally microbial focused. However, they can focus on DBPs and other things like harmful algal blooms and the distribution. But in Oklahoma, we've stuck to the traditional CPEs and then have done a couple of DBP focused CPEs. But what we've learned is that when you add the DBP element, it takes a lot of additional time and staff to complete. So when you have staff turnover, you're really focused on getting them trained in that microbial CPE, and that can also make it difficult to add the DBP element. But it does allow you to collect a lot of data and help those systems out that are having DBP problems. Now, I talked about a small part of AWOP that is enforcement, and that is the CPEs. You can have a CPE triggered, mandatory one triggered, and it's a mouthful for that trigger, but if the same filter exceeds 2 NTU in 2 consecutive 15-minute periods in 2 months, that water system has triggered a mandatory CPE. So we try to do as many voluntary CPEs as time allows, so we're sharp and we are up to date on the process if a mandatory CPE is triggered. And since 1999, we have performed 31 CPEs in Oklahoma. I had updated this on my presentation, but it's actually 5 mandatory CPEs that we've done, and 4 of those 5 have been done in the last 5 years. And then we've done 2 multi-state CPEs in Oklahoma, and that's where other states from the AWOP program come and join us on our CPE and get to learn from our processes. And we've also done 5 multi-state CPEs outside of Oklahoma, where we get to go to other states and learn from them. Next slide, please. Performance-based training, known as PBT, it's a very different setting and structured differently than the CPEs. And it's multiple trainings that are in a class setting with a group of public water supplies. Approximately 4 to 6 is kind of the ideal size. And there's trainings are spread out over a year to year and a half. And in Oklahoma, we've done PBTs with a DBP emphasis. And like I said, it's a year to year and a half to complete. So it does take dedication from the state regulators as well as the water systems to go through the program and complete all the different modules. We focused on PBTs between 2006 and 2009, and during that time we were only able to get 11 systems to complete the program, and we asked probably more than double that to participate. And some did come to a meeting or 2, but then they did drop out. The good news was for the 11 that completed it, they all showed an improvement in either THMs, HA5s, and or TOC. And we did have a few that showed improvements in all 3. So it was a very successful program. Next slide, please. AWOP Awards. This is near and dear to my heart. It encourages optimization by recognizing participating public water supplies. It started in 2019, so it is fairly new to Oklahoma. We've had to cancel our 2020 program due to the pandemic, but we are gearing up for 2021. And my pictures aren't on here that I had added, but we do give out for the awards for the top systems, a flag, a trophy, and even a certificate plaque type thing for the participants. We are allowing all public water supplies to participate because any system that's interested in optimizing, we want to make sure and help them and recognize them for that. They have to meet certain criteria to get points, which includes various optimization goals, as well as things like capacity development assessments and water loss audits. The 4 categories we have are surface water, groundwater, purchased water, and non-community water systems. Next slide, please. And the final area I wanted to cover as part of our AWOP program is the DBP pilot project, which is a compliance assistance project that emphasizes monitoring and training. Now, EPA came to Oklahoma and asked DEQ if they had some funding, and would DEQ be willing to help facilitate this pilot project. And of course, we wanted to do that and help our water systems. So EPA contracted with a company called Process Applications Inc., PAI, and together EPA, DEQ, and PAI are trying to execute this project. And the first part of the process emphasizes collecting and evaluating data to assess performance, and then it's followed by implementation and evaluation of special studies. It is similar to PBT, except we're very focused on certain groups of water systems in the state, and it's not going to last quite as long. Oklahoma decided that we could most effectively help systems with this project by picking 4 combined distribution systems, which includes the wholesale system as well as the purchase systems. And we chose 4 in the eastern part of the state, and those 4 CDSs had a total of 32 public water supplies. We were able to get 31 of those to agree to participate in the program. It includes 2 in-person training sessions and 2 follow-up calls. And we just had our first in-person training session the week of August the 17th. We also allowed participants to join remotely due to the current circumstances. We were able to get 22 water systems to participate in that training, and we would have liked to have seen more of those 31, but the ones that did participate, we felt overall it was successful. And we'll be doing a follow-up call in October, followed by a second in-person training in November. Kansas and Region 7 is doing a similar project. They're targeting different water systems. The 4 CDSs we're looking at are all free chlorine with primarily THM violations, because those are easier to handle through optimization. Excuse me. But Kansas is looking at different types of water systems, different types of disinfectants, and they're doing it completely remote. So we're anxious to compare notes with them and see how their project goes, and also see how our project goes. Next slide, please. Okay, now we're going to switch gears and start talking about the Drinking Water State Revolving Fund. What is it? Well, states provide low-cost loans and subsidy for public water supply assistance, which includes construction, small system technical assistance, and various administration of the DWSRF public water supply and capacity development programs. An EPA awards yearly grants to each state based on assessed need and available funds. The need is assessed through needs surveys, which occur approximately every 4 years. The last needs survey was done in 2015, so we're a little bit behind, but we're gearing up to get going on the next survey. Back in 2015, the needs survey indicated that Oklahoma alone had just under $7 billion in water infrastructure needs, and nationally it was $473 billion. That's a lot of need. We do cooperatively administer the DWSRF program with Oklahoma Water Resources Board, and we do the technical side of the program, and the Water Board does the financial side. They're kind of like a banker for the program. And since the program began in Oklahoma in 1998, the DWSRF program has financed 205 drinking water projects for over $1.391 billion. Next slide, please. So I wanted to focus on the DWSRF health-based subsidy. And back in July of 2018, we transitioned from a regionalization focus for the subsidy to a health-based focus for compliance assistance. We do emphasize DBPs because of all the health-based violations for them in Oklahoma, but systems with other health-based violations can qualify for the subsidy. This fiscal year, we have $2.18 million in subsidy to use. And to qualify, you have to be a non-compliant public water supply and signed a consent order, as well as paid the penalty. Next slide, please. So to reach out to the water systems, we did some DBP subsidy meetings. We invited groups of systems to DEQ and presented an overall presentation and then worked with them individually. My manager developed a prioritized system by an in-out method where we start with the wholesalers that have purchasers that are out of compliance and that those violations are affecting the highest populations, and work with them and hopefully get the wholesalers in compliance to supply compliant water to the purchasers. And then we focused on systems that may not sell to anyone or purchasers that were out and their wholesalers were in compliance. Once we divided the systems up into individual tables, we had different entities go around and speak with the systems to let them know what was required of the subsidy and what kind of projects they might consider. So the water board discussed the financial aspects with the bond council, the project engineer, environmental coordinator, and program coordinator with the DWSRF would talk about all those requirements. Our compliance staff and our enforcement engineers also rotated to discuss the current enforcement status and let them know how important it was to move forward with this subsidy and hopefully use it to attain compliance. Next slide, please. So I wanted to talk about some subsidy details. We allow $100,000 per water system for the health-based subsidy. Now, we did have a consulting engineer approach us and say, hey, if the purchase systems are out of compliance too, can they contribute their subsidy towards the wholesale system for its project? And we considered that and said yes, if that project will also help the purchasers attain compliance. So a system I'm working with is converting to chloramines as part of their DBP subsidy project. And they were able to get 5 of their purchasers on board to contribute their subsidy money towards them for the project. So they have $600,000 in health-based subsidy to use for that chloramines project. The subsidy may be 100% or a portion of the project, and it can be incorporated into an existing project. If a system's already gotten started and just heard about the subsidy and wanted to use it, they could, but they have to be careful because you still have to meet DWSRF requirements, and depending how far you are along, it can be difficult to go back and meet some of those. Now, the funds will go toward all eligible project costs, including special studies. And special studies can include things like THM formation potential, hydraulic modeling, storage tank detention times, and also things like if you're wanting to do GAC, the rapid small scale column test, all kinds of things for special studies. It's really important, as I'm sure most of you know with DBPs, to understand what the problem is within the system, because every system is unique, and how those DBPs are formed and what the proposed project really needs to be. We also have a separate pot of money for investigative sampling. So we've encouraged systems to contact us, and we'll go out and take samples that we do submit to our lab for compliance value, or it's non-compliant samples, but to understand those values, just like they were submitting compliant samples in their system. It can be combined with disadvantaged community subsidies. So the system I was talking about that was converting to chloramines, they got an additional 100,000. So then they had 700,000 to contribute to their project. So it was a good chunk of their project they got with subsidy money. They still have to meet DWSRF requirements, as I said. That includes things like having a resident inspector, the Oklahoma Competitive Bidding Act requirements, Davis-Bacon, American Iron Steel, and more. We do require a DBP operational checklist be completed. This checklist incorporates a lot of the AWOP concepts and optimization ideas, and the operator as well as their engineer has to sign off on that. Initially, we required an engineer from a DEQ pre-qualified list. I'm going to talk about that some more in a couple of slides. We'll get into that in just a minute. Next slide, please. Some additional subsidy details. We don't require the public water supplies to get a bond attorney. This is through a special contract with the Oklahoma Water Resources Board, so it's no expense to the system, and they can maximize their subsidy funds for their projects. DEQ is doing the environmentals. We suspect most of them, if not all of them, will be CADXs. So far, they all have been. So that's another expense that this water systems do not have to worry about. The financial application is streamlined through the Water Board, and our Oklahoma Rural Water Association is also offering assistance for that. And we cap the local council fees at $2,500 and do not allow financial advisor fees to be reimbursed through the subsidy. Next slide, please. As I said, we'll talk a little bit more about the pre-qualified engineers list. Back in July of 2018, when we were kicking off the health-based subsidy program, we developed a committee to look at what minimum qualifications we felt engineers should have to work on these subsidy projects. And we did this because we were hoping to streamline the projects, allow the systems to attain compliance as quickly as possible. And we came up with normal, the normal things. You have to be registered, licensed PE in Oklahoma. But the criteria that hung a lot of engineers up and didn't get them approved was we wanted 1 DWSF project and 2 successful DBP projects where that engineer was the engineer of record. And we sent requests for qualifications out to all the licensed engineers in Oklahoma. We were required to do that. So we sent hundreds of RFQs out, and then the committee reviewed the statement of qualifications that we received back and decided if we were going to approve it, deny it, or request additional information. Next slide, please. So our list went up and down, a few times, but there was the highest number of pre-qualified engineers ever on our list was 14. And we provided this list to the water systems when they came in for the meetings. We posted it on our website, and we let the water systems as well as the engineers know, that about this requirement and who was on the list. And once we had our list going, we talked to the water systems and let them know that they had to solicit requests for proposals from at least 2 engineers on that list. And that became a little confusing for the water systems, but we helped them out. Now, a lot of the systems already worked with an engineer and wanted to retain their engineer. So if they had their engineer under contract before December of 2018, and that engineer was on our list, and the contract was for a DBP project, they could use that same engineer and not go through that RFP process. We did have a system that was adamant that they wanted to keep their engineer. He was not on our list, and so we allowed them to use that engineer, but we were not going to reimburse the engineering fees with the subsidy money. Next slide, please. So as I said, we started the subsidy for the health-based violations back in July of 2018. It's been over 2 years. We were really hoping, we were working so hard, had all these ideas to get these projects streamlined and completed, but we've only closed 7 loans, and we have 2 that are pending. And one of those 7 projects has been completed. We have a couple more that are very close, but it's not as many as we had hoped or wanted to see. But the ones that we have seen and have come in and we've been looking at include separate inlet and outlet, mixing, aeration, conversion to chloramines, and some other things as well. Next slide, please. So most importantly from these processes, I wanted to talk about our lessons learned. I don't have it on this slide, but I wanted to say with AWAP, I think we've learned that it is successful for compliance assistance, but it does take a lot of time, effort, dedication, and staff to implement it successfully. And sometimes it can't always be the priority depending on what else is going on. Now for the health-based subsidy, we discontinued the pre-qualified engineers list just back in July of 2020. And we did this because a lot of the engineers we're typically seeing submit projects to us, they didn't qualify for the list. They weren't the engineer of record for a lot of the projects that they had worked on. And so we heavily loaded the engineers that were on the list with these DBP subsidy projects, and it was slowing the projects down because the engineers just had too many projects. And then the requests for proposals that the water systems were supposed to do, as I said, they were really confusing. We would try and help them and give them templates and things like that, but it was difficult for the water systems, and it was also slowing the process down. So we have discontinued that list. Also, we're seeing the consulting engineers place minimal emphasis on using the subsidy for special studies, which is just very frustrating because the projects that we are getting, we're wondering, how did the engineers determine those projects? Most of these systems are very small and may only have 1 or 2 sites that they're sampling for compliance every quarter. It's not a lot of data to use to make a decision. So we hope we'll get more projects where the engineers take time to use that money for doing some special studies before they propose solutions. And the subsidy was really meant to supplement DBP projects for compliance. The goal of the subsidy is compliance. So we started seeing a lot of aeration projects because the engineers would promote that they can get, these small systems can get a free project, engineering, resident inspection, construction, all for $100,000 or less. And aeration, again, you may need to do some special studies to see if it's going to work. And even if it does work, it may only help a certain part of that water system, where we want the water system looked at comprehensively and attain compliance for the system. So that's been a bit frustrating. The DBP operational checklist is not being thoroughly completed. The operators tend just to blanket check mark yes, 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 and the engineers sign off on it. And as we talked about before with AWAP, that if you really look at this list and optimize your system, you can maximize your funding because you can put it towards the things that you really need it for. You've tried operational strategies, and this is the infrastructure that you need. So the list is really important, and I think it would be more successful if we got operators and engineers to buy into it more. And then the reviews are taking a lot more time for the project engineers. Part of the problem is, I mentioned a separate pot of money to do some investigative sampling. We'll get things proposed that, we're not sure is going to work. So we have to stop the project and say, we're going to use this investigative money and go out and take samples. We'll provide the data to the consulting engineers so they can make sure and provide a successful project, propose a successful project to us. And then for all these reasons, the projects are taking longer to start construction. We're not seeing as much movement as we hoped, but we need to get that subsidy money out. So we have added regionalization back to the subsidy in July of 2020. We just need to be careful that by promoting regionalization, we're not creating new DBP problems in the state. So we have to look at that closely when we're reviewing these projects. Next slide, please. This is my contact information. For questions, I'll be on the panel later, but feel free to contact me at any time with any questions through phone or email. And this background slide here actually was taken by a coworker of mine when we were up in the panhandle of Oklahoma. So if you've never been to Oklahoma or curious about what it looks like, this is what the panhandle looks like. It was a beautiful, very cold January morning. We were headed to Hooker, Oklahoma for an AWAP awards visit as well as a DWSRF visit. So I think this really represents the beauty in our state. But thank you so much for your time today, and I will pass it back to Alan. Thank you.
Thanks, Kendi. I appreciate you closing with that shot of the panhandle of Oklahoma. It had some relatives in Diamond at one point, so I've been in that part of the country. And so with that, we'll transfer to our last speaker, Stig Regli. Stig is a science policy advisor in the Office of Groundwater and Drinking Water at EPA downtown in DC. And Stig and I have worked together for many years on DBP microbial issues. I consider him to be both a really smart guy, practical, able to solve some of these complex problems. So with that, Stig's going to talk about challenges in controlling DBP risk in small systems. So take it away, Stig.
There we go. Can you see the screen, folks? Does that work?
Yes.
Let me get the slide. Just hold this. Slideshow view. Wait a minute. I want to get the.
That's right. It's slideshow.
Slideshow. Is it showing now? I mean, is it?
No, go back to slideshow.
Yeah. There we go. There. Okay.
And from beginning.
Yeah. Okay. Good. Okay. Very good. That should do it.
Looks great.
So I'm going to talk. Okay.
Good.
Share my. Okay. Click this here. All right. Are we on board? I'm seeing
Yes.
myself.
We're on board. We can see you on the slides. Proceed.
Okay, fine. Okay. All right. So the title of this talk is Considerations and Challenges for Controlling Disinfection Byproduct Risks in Small Systems. I want to acknowledge Jimmy Chen. He was a co-developer of this presentation. And let's launch right into it here. Just first as a disclaimer for us that the views expressed in this presentation are those of me and do not necessarily reflect the views and policies of EPA. The other disclaimer here is that I'll be showing some preliminary results from the UCMR4 analysis, and they're preliminary, and they will be subject to further revision as more data comes in. So keep that in mind. The overview of this the objectives of this presentation is to provide a perspective on considerations and challenges for controlling DBPs. This is going to be a very high brush characterization of these perspectives, including some initial observations from the UCMR4, and then a characterization of differences between small and large systems on DBP precursors, treatment technologies in place, and DBP occurrence levels. So the challenges, these are historical in nature. Ever since I've been working for the agency for many years, and this issue of challenge with controlling the micro DBP groupings has been with us for the onset, the very initial rules. Risk trade-offs regarding the microbes and DBPs, that's obvious. The second one has become something that is become more informed with time, and that relates to if you control for one group of DBPs per, let's say, an MCL like THMs, then you have treatment responses to that create different mixtures of DBPs. So we want to be aware of those potential implications. The other major challenge relates to the complexity of the water supply systems. This relates to their source water challenges and the range of existing treatment processes, which are largely dependent upon the source water challenges, as well as their distribution system configurations. And then lastly, on the complexity, there's a recognition of very large economies of scale for large versus small systems. This relates to the household cost, for example, of what might be incurred by a system if it were to install a treatment technology in response to a particular regulatory target. So we're recognizing these economies of scale. All of these complexities are part of our challenge for controlling this suite. And I'll be focusing mainly on the DBPs. The other piece here is the uncertainty and data gaps. This is something that we're always challenged with, but we have different capacities to deal with them as we learn more. So noteworthy regarding the challenges are consecutive systems. Many of these systems have much longer detention times than the distribution system, so that allows for further formation of disinfection byproducts relative to the water they may be receiving from the delivered the system delivering that water. So this is an area that has received a lot of attention by EPA. EPA has an in-depth analysis of the drinking water rule implementation report, and there it identified the stage 2 as having the most MCL violations among all the different rules. And this is particularly noteworthy for the consecutive systems. The other noteworthy aspect of this report relates to the area-wide optimization program. You've heard already a lot about that. I can't say enough of this. It's a wonderful program, and it has great opportunities for helping systems comply and enhance their current capacities to meet different targets. So this is a diagram on slide 6 here. This is a diagram of the portions of the community water systems with health-based violations as of fiscal year 17 by rule. And so you see on the right-hand side, this is the right-hand side pertains to the MCL violations. The left-hand side pertains to the treatment technique violations, all health-based violations. So it doesn't include reporting, monitoring violations. Noteworthy here is that the stage 2 is dominating the space in terms of the relative numbers of violations among the different MCL regulations. And this is a characterization of how the violation rates compare among the consecutive systems versus non-consecutive systems. And you can see here that there's roughly a 3-to-1 ratio of non-compliance among consecutive versus non-consecutive systems. And most of these are among the very small systems. Now, the area-wide optimization program, I think I can skip this because Candy covered a lot of the ins and outs of this. Again, I just want to indicate my long-term history and involvement with this, and it's a program that's evolved and become more and more, I think, comprehensive in how it's looking at problems. So there's a lot to be learned from various webinars that have been given on this. And you see a website below that you can refer to for further information. Now this slide here is showing the timeline of the DBP rules and data collection. This is mainly a characterization of occurrence data that we consider when we develop new regulations. And we try to understand the baseline of what's going on subsequent to the compliance of a particular regulation. And what you see here is a fairly significant time lag between when regulations are promulgated, when the compliance monitoring begins, and when the data that becomes available from those compliance monitoring efforts are able to be analyzed. So this is an ongoing challenge in terms of lag time and processing of information. The other noteworthy aspect of this slide is the UCMR4, which I'm going to talk more about later in greater detail. But this is an ongoing effort where we're getting monitoring occurrence information for the haloacetic acids and precursors and so forth to be described in a little more detail later. The other piece that's on this slide is the 97-98 data set for the DBP information collection rule. We still look at this for looking at relationships between source water and treatment and formation of DBPs. And this was a vast gathering effort that came out of a negotiated rulemaking that pertained mainly to the larger systems over 100,000 people. So that's some of its limitations. As we get more data to inform small system occurrence, we begin to understand better some of the initial assumptions we made on that small system occurrence. So the 6-year review 3, which was completed in January of 2017, we identified in this effort various candidates for potential revision. So here in this slide here, you see the microbial candidates for revision and the different rules that are under review. Not noted in this slide is the long-term 2 enhanced surface water treatment rule. And one of the reasons for it not being included here is that the round 1 of that monitoring indicated much lower cryptosporidium occurrence levels than we initially had, and there's a round 2 monitoring effort underway. So the review of this these regulations for under the 6-year review pertains to these different rules and their criteria therein. For the DBPs, here we are looking at the regulated DBPs, chloride, haloacetic acid, and total trihalomethanes. These are all candidates for revision, and they are embodied under the stage 1 and stage 2 disinfection byproduct regulations. There's also a report that fairly recently, 2018, came out by the National Tox Program that recognizes 4 of the unregulated haloacetic acids as being reasonably anticipated to be human carcinogens. So this is fairly recent information that we didn't have further back when we were contemplating an HA9 metric for the haloacetic acids, but we didn't have enough both occurrence information, and we also were looking for more health effects information. So this recent report basically recognizes the likelihood of the 4 unregulated haloacetic acid being human carcinogens. In this slide 12 here, you see the different monitoring information under the UCMR4. We see this as a wealth of information where we can learn a lot. We haven't had previously, since the DBP 9798 ICR, much national occurrence information on these the unregulated haloacetic acids. So here we have those as specified under the rule to be monitored differently for surface or groundwater systems, the frequency, and then also the precursors of bromide and TOC in the source water, as well as disinfectant type and treatment processes within the plant and distribution system. So there's a wealth of information here that we're just beginning to unravel based on the preliminary information that's come in. And we anticipate this contributing very much to our understanding about implications of what we might do for the haloacetic acids. And there's also a desire to ultimately have some linkage with the THM occurrence information that will be available under the next 6-year 4 review. Here you see a table, this is slide 13, which lays out the different categories of haloacetic acids as they pertain to both those that are regulated and unregulated. So the last 4 rows include the 4 unregulated brominated haloacetic acids, and you see 4 of those are included in the HA6BR, and then as well as in the HA9BR. Those are the groupings that were required to be reported on under the UCMR4. So we're getting a sense of what these different groups are, and you can do different types of arithmetic to understand relative contributions of the unregulated versus the regulated. Now this slide 14 is showing the current data that we've analyzed to date from the UCMR4, and the noteworthy here, this is data that was released in January 2020, so there's a lag time for the analysis and what we're looking at before we are able to put it in a form of characterization. Noteworthy here is the difference between the numbers of samples that are, or the numbers of systems that are implicated under the UCMR4. You see the lower row, less than 10,000 people. That's a sample set that is intended to be representative of the US, and the system size over 10,000 is basically a census. All the systems that are required to comply with the DBP regulation are included if their system size is over 10,000 people. So we have roughly a third of the large system and a rough of the half of the small system data that we anticipate ultimately being available for analysis. So the results are preliminary. Based on what we've seen so far, we're noticing certain relationships of this data, and that is that the concentrations between small and large surface water systems of the halo acid groupings appear to be relatively small, whereas in the groundwater, among groundwater systems, the larger ones tend to have higher haloacetic acid concentrations than the smaller groundwaters. And this, we think, relates to the bullet below, the last one, or the sub-bullet, where large groundwater systems tend to have higher TOC than small groundwater systems. And this, we think, relates to the yields. These large groundwater systems have larger yields, and many of them are perhaps inundated with infiltration of organic materials. Florida is the prime example of large groundwater systems that have very high TOC. So that is not surprising, these preliminary observations. And then in general, and this is a very important finding that is supporting some of the historical understanding, is that the groundwater systems tend to have a higher bromide have much higher bromide and lower TOC than the source waters in surface water supplies. So that has an implication in terms of the formation of the extent to which brominated chlorination DBPs, be they THMs or halo acids, might be significantly different among groundwater systems versus surface water supplies. And we'll see some of that in some of the subsequent slides that I show here. So this is a slide 16 that gives you a picture of how we're looking at the data from a national level. And it's based on this partial UCMR4 data set that is indicating that the groundwater systems, if you look at on the right-hand side, you can see that the curves, the three curves that are representing the different categories of haloacetic groupings, HA5, HA9, and HABR6, that they are significantly to the left of the surface water systems, showing that, you know, they have much lower levels in general. Now, there are some exceptions in terms of some of the groundwater systems. Large have these higher levels that are comparable in many situations to surface water supplies, but the relative distribution of these categories of systems is significantly lower for groundwater systems than surface water supplies. The difference becomes less when you look at the brominated specific category, HA6BR, and that relates to the understanding of the different ratios of bromide to TOC and the formation effects of that. Now here you see, this is slide 17, you see a slide of, this is listing the 8 small surface water systems with the highest bromide levels in UCMR4. Again, this is a relatively small sample set relative to what we will have when the UCMR4 data set is totally completed. But you can see here some features that are revealing. The highest, the two systems that have the high TOC, 1 and 3, have significantly different concentrations of the haloacetic acids among the different groups. And this, you can go down to the lower part of this table on the treatment side. You can see that this is surface water system 1 has slow sand filtration and membrane filtration. So you've got a lot of precursor removal that would take care of a lot of that organic material. And then you have a preoxidant of chlorine dioxide, which is going to be preventing some within plant formation of the halo acids. And then you look at surface water system number 3, and you see a less rigorous removal of precursors, and that is a good explanation for the high differential between the haloacetic acid concentration levels. I think an interesting feature here is the TOC level of the number 8, where you have slow sand and GAC together, and they are able to have still relatively moderate concentrations even with chlorine, and so they have the combination of slow sand and GAC, which could be contributing to that. Okay, let's look now at these small 8 small groundwater systems that with the highest bromide levels in UCMR4. This is reflecting from high to low in the column 3 of the bromide. And here you see the TOC concentrations that correspond to these bromide levels in their source water. And noteworthy here are the use of membrane technology. Those levels, bromide at that level 5,000 and TOC, are very, very, very high. They're much higher than historically we've had records of. So there's something that is happening to this particular system apparently, but they're using membrane technology and they're using chlorine and then chloramine to keep their levels moderate. And then you have another situation where system level number 2 is an interesting. They indicate they have membrane filtration technology. Why is that? Well, we think that they have other contaminants there that have made them elect to use the membrane technology to then deal with that those synthetic chemicals. So this is something that looks like perhaps an anomaly of why they have such low TOC and why they're installing membrane filtration. So we tend to explore further what we can understand as the data set becomes more complete and as we reach out also from with our stakeholders about some of this information. Now, in summary, these consecutive systems are the consecutive systems tend to have higher concentrations of DBPs than the non-consecutive systems. There are differences. It's not a generic relationship that you can just say that pertains all the time, but there's a tendency for that to occur because of the higher retention time in the distribution system. And then the UCMR4 data set, that is something that is going to further inform the HA occurrence and associated conditions, the source water, precursor, and treatment. As I've indicated, we look very much forward to getting that additional data in and then doing a more complete analysis. And then the UCMR4 data set is going to be further analyzed and will shift, no doubt, some of our initial interpretation. So we have to take what we've presented with a grain of salt. And then lastly, I want to say something about our next steps. So we're following up with this 6-year review process and gathering additional information to inform possible revisions to the MDBP rules. And this is a big deal to try to sort this out, the complexities that I talked earlier about, and also the consideration of the unregulated DBPs because of the trade-offs that might occur if you target the regulated, what happens to the unregulated. So we have to be sensitive to those unintended consequences. And we also have to be sensitive to the challenges pertaining to the small systems, including these consecutive systems. We're very much going to be considering that in the framework of the consider options for going forward. And lastly, well, not lastly, but we are planning to seek a lot of stakeholder input to help inform these the possible revisions that might come out of this effort. Historically, stakeholders have been instrumental in shaping what we ultimately develop as final rules. And that process of recognition of that sensitivity is very much alive and appreciated within the agency. So EPA anticipates to publish a proposal to revise the MDBP rules by July 24th, and with that strong consideration of additional stakeholder input. So with that, I turn it over to Alan, and just say I'm very grateful for having this opportunity to present, and also gratitude for my colleague Jimmy for working together on putting this together.
Thanks, Stig. That was an informative presentation on the what you found so far with UCMR4. I'm sure we'll have more to come as EPA fleshes out that stakeholder effort. So I'm going to kind of go back and forth. I've had a bunch of questions. Some I've been able to answer individually in the chat box, but some I think warrant some discussion. So if we can get Nelson and Candy to unmute, then we can, and maybe put their camera back on, we can go through these questions. We've got about 25 minutes here before we'll take a break before the next panel start up at 3:30. So Nelson, let me start with you, and I think I can answer part of it. So the question came from Eric. Have you ever evaluated water quality changes due to demand or seasonality? So demand, you kind of had that in there with the different time frames that you used. You had 3 different windows, so that takes care of how the demand can fluctuate. But was this done over a long period of time, or can you talk about seasonality a little bit?
Sure. So seasonality, I didn't directly consider it in this study. It's definitely something that needs to get covered in the future work. Because as we know, our systems, they change throughout the year. So I was using kind of one representative week. But for the future, it's definitely something that should be considered.
Are you going to be able to fit that into your PhD research, or do you need to graduate at some point?
I think I might graduate before that, but somewhere along the way.
Yeah, someone else at Amherst can pick it up if need be, because it's an interesting question. So another one for you, Nelson, and then I'll work my way down the panel. So given iron and manganese interference with chlorine results, have you considered correction factors for your model of systems that may have those kind of iron and manganese issues?
Sure. So I didn't directly do that here either, but in terms of options for how to handle that, in terms of correction, perhaps, is I just used EPA-Net 2. If I were to have used EPA-Net MSX, the multi-species extension, then that allows you to have interaction with different factors. So like you're saying, the manganese and the interaction with chlorine and everything, you can have those accounted in the EPA-Net multi-species extension. Yeah,
that would probably add a fair amount of complexity to your analysis.
Definitely.
Probably more a bigger model, takes more time to run the whole bit.
Mm-hmm.
Yeah, that could be your second PhD, I guess. So last one, I think, for you, and then maybe we'll work our way down the. So you know, you had the different approaches. You know, all nodes, geographic, the FAR 20, the dead ends. Did you do? And I don't. This is a statistics question, and so I'm not sure if you even looked at it. It was more just the way the different frames that you used. What are the minimum number of nodes needed to confidently use this model and this data for water quality decision making?
I really can't give an exact number on that. I will say that the models that I did use were fairly detailed. I think if you were to have a smaller number of nodes and compare it to the number of samples that need to be taken, it could be a little more difficult if there's not that many nodes in the EPA-Net model. But there are probably some ways that it could be addressed.
Yeah, it didn't even seem with like the FAR 20 and the dead ends, just the map that you showed, it showed a lot of dots. So
Right.
it wasn't like you had 5 samples, you had large numbers in all of them. So let me switch maybe to Candy for a minute, and someone asked a question about the hydrant samplers. Are there several manufacturers? The question came in from Rory. Is there a link or a list of these hydrant samplers? Are you aware of that?
Yes, it's actually provided by the National Optimization Leadership Team. They've just come out actually with an updated hydrant sampler parts list, and I don't know if there's a place I could post that for everyone to access. I'm certainly happy to get it to anyone that's interested if they contact me. It gives you a detailed parts list, and it's not too difficult to put together, but you have to buy those pieces and construct it. I don't know of any you can just go out and buy.
Okay, but it's a manageable project for someone that's reasonably mechanical to be able to do it. So,
Oh yeah,
as I say, yeah, but yeah, that'd be good. I mean, go ahead and people contact her, or you could also contact me, and Candy, you can send me the list too. I'm curious exactly how much work it takes to do. So we've got a couple questions that came to you about chloramination. And what size was that system that was proposing? Bill asked for the systems that were proposing to convert to chloramines. What size were those systems? Were they 1,000 or 10,000 or some kind of all over the map?
So that particular system, it's a system just over 10,000 in population. It has, I believe, a total of 7 water systems that purchased from it. And most of our large systems in the state do chloraminate to deal with DBP issues. And this system just tried some other things that haven't worked, so they're going to go to chloramination. We don't have very many small systems chloraminating, which we think is a good thing. We don't allow it for primary disinfection in Oklahoma, so most systems have to use free chlorine for their disinfection credit anyway. And if they can manage their DBPs with free chlorine, we definitely encourage that. But chloramination can be approvable for any size of system.
So just drawing into that a little bit, the chloramination. So was that system or the consecutive systems, were any of them in violation prior to the switch? Were they just getting close up against it?
So we've just started construction with the chloramination. So I'm not sure. We suspect after they begin chloraminating, they'll be in compliance after several quarters. But all of the systems that purchase and the wholesale system is out of compliance with DBPs. And the wholesale has been out since stage 1 and even before then, because they were a large system monitoring THM. So they've been out of compliance for a long time. They've done several projects trying to address it, and then finally they're at this point of converting to chloramines. And of course, we're monitoring it closely too, because we know that can change their water quality and cause corrosion issues and all that. So it's a tough decision to make that change, but we're working with them and hope that it will be successful for them as well as their purchasers.
One last question. Your neighbors to the south in Texas, I know require nitrification. I don't know if they call them management plans or action plans, but they have, they'll want the systems to monitor for these other parameters on a regular basis to try and see if they can get the start of nitrification, and they monitor more frequently and try and do what they can to prevent that. Does Oklahoma have that, or is that something that, how big a problem is nitrification? You have warm temperatures there, I know, again, because grew up there and the summers were just hot. And so you get good water temperature. It is hot.
Yeah, we're getting a break today with some rain, but yes, it is very hot in the summer. And we work closely with Texas in the AWOP program, and we've learned a lot from them, in regards to chloramination. We don't have the strict requirements that they do in monitoring and distribution. We do have systems do an engineering study. It's a six-week study prior to conversion to get a baseline of how things are in the system before converting. And then we have them do for 1 year some quarterly monitoring, and then following that we have them do some annual monitoring for things like HPC and free and total chlorine and bacteriological samples. And so definitely Texas has beefed it up, looking at monochloramines out in distribution and looking at nitrates and things like that. And we've looked at what they require, and we're hoping eventually to incorporate some of those same things in our rules, because we do systems that have chloraminated for a while, it takes several years, but we do see nitrification issues, especially in those purchase systems that are monitoring and even doing less than those wholesale systems and don't have any control over that ammonia chlorine ratio. So we suspect in the future it will create a new problem, and we're going to be there to try and prevent that and help, work through it with them.
Yeah, it's good to hear that you're collaborating with Texas, and I figured that because the way the AWOP program works, when you have those regional meetings and people sit around, not only are you talking about it, but then you go out to dinner, you'll meet for breakfast, and these conversations seems to happen a lot, and even outside of the planned topic of the meeting, just given the structure that they are. I've been to a handful of them, and I've been impressed by the exchange information between the states. So a couple more questions. The question about does Oklahoma DEQ, and I know Oklahoma DEQ is not a giant state, kind of in the middle, and talking with Shelley, who's the current ASDWA president. Do they meet with the engineering of the system throughout the project, like kind of cradle to grave all the way through construction and startup?
I want to clarify the question. Are you asking if representatives from DEQ meet with the system throughout the project? Or
yeah, just like how much hands-on you do after you give them the loan and stuff, because you're not a huge program within DEQ, so you can only, your face-to-face time with these systems engineers has got some limitations of what you can do and can't do.
Oh, definitely. Through the DWSRF program, if it is a project through us, through the health-based subsidy or just a loan or any other subsidy we offer, the system is assigned a project engineer, and that engineer stays with them from the very beginning all to the end. And we make, with the exception of what's happened through the pandemic, the process traditionally is that we make monthly inspections, and during those inspections, we also have meetings that include the consulting engineer, the water system, the resident inspector, the contractors, and we sit down with them face to face every month and interact with them, and then go do an inspection at the site. So we are as hands-on as we can be, and of course those inspections are so critical, and especially those meetings, because things come out, when you're sitting there face to face talking, that you never hear about through emails or on the phone. And so it's a really important process, and that's something that we try to promote with our program, is that we're there, we're advocating for the water system, making sure the project is done correctly. We want them to achieve compliance and maintain compliance, so we want to be as part of that project as much as we can be.
Yeah, I think the monthly meetings is something I know the folks at Virginia Department of Health, the primacy agency where I live, they have a SRF team, and they do the same thing. Again, same reason, very helpful to be out there. So last question for you. Well, I have a couple more, but one question I'll branch over to Stig. So is the subsidy, the DVP subsidy that you have, only for small systems at less than 10,000, or you talked about that one that was just a little over 10,000, but it's not something you'd see for like Oklahoma City or Tulsa or anything like that, right?
We haven't necessarily put a cap on population for the health-based subsidy, but in Oklahoma, most of the systems still struggling with the DBPs aren't going to be over 10,000. This particular system, like I said, has struggled for a long time, and they're finally converting to chloramines. But the systems we traditionally work with, and those COs that I talk about, the 108 COs we currently have for DBPs, most all of those are going to be for systems under 10,000. But we haven't put a cap on the population for the subsidy. The disadvantaged community subsidy I briefly mentioned, we are focusing on small systems, but we're not saying large systems can't get it. It's just we're prioritizing those small systems for that subsidy. But for the DBP one and the health-based one, we just want to get systems in compliance no matter what their population is. And like I said, for us, maybe if there was a lot of large systems out of compliance, we would reconsider that to prioritize the small systems with more financial issues, but that's not a problem we're seeing, so we decided not to do that.
So I want to ask a question, and I'll ask you, Kenny, but I'll also switch to Stig to get his answer. Is the issue of aeration for DVP control, and again, I'm not an expert on it, but I know it works better for the chlorinated DVP, so chloroform and things like that. Strip that out, which will leave the brominated, which will reduce the total number and might put you in compliance, but now you're leaving more of the ones that technically might have the more adverse health effects. And I don't know, have you seen that in the before and after, or did you get some reduction in all of them, or what's your perspective on that?
Well, that's an excellent question, and there has been a lot of debate about that during AWOP meetings as well as at DEQ, because working with Texas especially, You know, what we've learned is that you can aerate brominated species, but it takes a lot of energy, which can be very expensive to do. And, you know, so we primarily focus on systems that have the non-brominated species. We feel like that will work more successfully, be easier to achieve. And some of the other issues we see is when you start going in to the brominated species and it does require more energy, is getting adequate ventilation. We're getting a lot of pushback from consulting engineers trying to propose aeration for brominated species. And we've, you know, tried to educate ourselves as well as them on what may or may not work. And we've gotten 2 projects proposed. It hasn't been installed yet for aeration where the systems primarily have brominated species, and we're asking for some additional sampling, and we're going to kind of see how it works out. And, you know, we talked to them thoroughly to make sure they've taken that into consideration. So we're anxious, even Texas, everyone in the AWOP community we work with is really anxious to see the results, you know, of these projects. So we'll kind of see how it goes.
Stig, you have any input on that too? I mean, brominated is one that we've been talking about for years. I'm curious to get your perspective on it too.
Sure. Well, I think I like Candy's recommendation of considering the bromide levels and seeing the implications on the speciation. Obviously, it's probably going to be more conducive to reducing like chloroform and the in particular. So if you have low bromide levels in your source water, then it may, and you have difficulty meeting the standards, that could be a reasonable option. But I would caution its use if you have high bromide levels in the water, and then perhaps possibly even the increase of the brominated species. So you may not get much reduction of the brominated species with aeration, and so that's the question mark. You may be meeting the regulatory target, but and that becomes an increasing area of concern as we learn more. You know, you saw the NTP characterizations on the brominated non-regulated halo acids. Of course, those would not be that affected because they're not as prone to, you know, they're not as volatile. But altogether, I think sensitivity and caution, looking at the big picture and evaluating how relative the changes are in the brominated versus the non-brominated species should be a factor in considering.
Yeah, good answer, Stig. And there's one here that I'm going to answer, Stig, and you can correct me if I'm wrong, but Catherine asked a question. The question was, will there be a new DBP rule in July 2024? And the short answer is no. If EPA determines through their information collection, there's a requirement to propose by July 2024, there's an additional court date to go final in their recent settlement earlier this year with some environmental organizations. And even those dates can slip if EPA decides. There's some specific clauses in the court settlement that gives EPA more time if they decide to use a FACA or REGNIC process for this rule, or if they decide to do another information collection rule like what they did in the late 90s as part of this. The court agreement allows for different extensions. Stig, did I characterize that correctly?
I'm very laudatory of what you just said. I mean, you're resonating totally with the situation. So, yeah, what you saw on the slide was a proposal, and so obviously that's a factor. It takes time to promulgate, and then there are all these caveats as well that could feed into needing more time, but to maybe allow a more thorough characterization before going forward. So that was well stated, Alan. Yeah.
Well, just out of coincidence, when you were talking about it, I went back in my notes from when I got the call from the gentleman in the standards division about the dates, and I found my notes when I wrote them all down, so it was pretty fresh in my memory from about 10 or 15 minutes. When your slide popped up again, I was just trying to make sure that I had it right. So it's a court settlement. It was posted. We wrote about it on the ASDWA news blog when it came out several months ago, and the court settlement is available online through that. So. Stig, I guess, I got a person asking about the status of NDMA regulation. I assume that would be in the mix with everything that will be talked about as part of this information collection effort.
That's right. I mean, NDMA, we had a preliminary regulatory determination where it was on the list, and then we decided because of the complexity of the mixtures of DBPs that can occur from different treatment strategies. A big shift to chloramination. We've seen that historically. So there is a recognition of wanting to understand what we can do about these. We basically deferred its consideration that came out under the 6-year review, and the 6-year review is further supporting the need to consider it. Now, how we go about doing that, there are many different options of looking at it, but yes, it's on the table for consideration, and we'll have to see. The interesting aspect, as you very well know, Alan, that NDMA, these are known carcinogens. From the animal data, they're stronger, and also there's the epidemiology aspect that supports their being carcinogens. It's a combination of those things, but the relative source contribution from our exposure to nitrosamine comes in much greater proportions from food. Now, that doesn't affect what we might do under the Safe Drinking Water Act, because we are required to do what we can to mitigate things that are a health concern. So the short answer, I guess, after my long answer, is that yes, it is being considered, and we'll have to see how the options for looking at it play out. And we'll be looking a lot for stakeholder input on this. It's on the table for consideration.
Yeah, and again, depending on how things sort out, one of the advantages if the stakeholder effort starts up soon is that we're getting more used to this virtual environment. It might allow a broader participation than what we had to do in the past when we were negotiating these rules. So another question for Cindy. How much do you factor in finished water storage and AWOP activities? Again, I've been to half a dozen regional AWOP meetings and talked about different things, but I'm sure it's been talked about. I just haven't been for one of them.
Well, one thing that was talked about recently, we just had our AWOP meeting last week, is there is a spreadsheet that can help determine detention times in storage tanks that some states are using more frequently than others, but we definitely talk about that in terms of using that spreadsheet and what it can tell us and the limitations of it. That was some of the discussion that we had last week, but we also talk a lot about aeration because so many systems are trying to use that for DBP compliance. So we do talk about storage tank issues. I mean, it's part of our discussion during our meetings.
And then one more question. When you have the aeration, do you require disinfection after the aeration tower for anything that might get introduced when it's open to the atmosphere again?
So we do not require that, but some places, we do require minimum chlorine residual distribution. So if adding aeration creates a problem with losing chlorine through the tank, that would be something that they would have to consider. We make sure when we're approving the aeration that the ventilation is properly vented with proper filters and things like that, so they're not bringing in contaminants into the storage tank. But it just kind of is on a case-by-case basis. As long as they are meeting that minimum chlorine residual, we're not going to ask them to boost the chlorine.
A couple more questions for you. One is, I think Amy from another state is interested in hearing about how other states are revisiting their distribution system evaluation. So everyone did the IDSC several years ago. Some states require periodic updates, but their rule allows it at state discretion, but wondering if other states have statewide programs for certain types of systems to ensure that your monitoring sites are appropriately located throughout the system.
We don't have a particular interval that we're doing that at, but when we work with the water systems, when our compliance coordinators and our engineers go out there, work with them, talk to them on the phone, and are getting a feel for where some of their sample points are and where they're having problems, we're going to look at that and make sure that they're sampling in the correct locations. But we don't have like I said, an interval where we're updating it every 5 years or 10 years. mostly on a case-by-case basis, and trying to work with those systems and make sure that they are sampling correctly in the correct locations. When we had those meetings for the DBP subsidy and brought those systems into our office, our compliance coordinators had maps to go over where they're sampling and making sure that those were proper locations. So that was one way that we were updating them through the subsidy program.
All right, last question for Candy. So do you require an operational SOP to be developed, post installation that chloramination? In other words, to try and help the system understand it's not as simple as they had when it was a straight chlorine before?
Well, that's a little tough as far as require. I mean, most of them are required to have one as part of the construction and the start, when they're starting it up and having an SOP for those things. But we highly recommend that the operators develop an SOP, once they get up going and operating and understand the demands on their system and what ratio they need to be at. But as the reality is, most operators aren't, even if there is an SOP, they're not looking at it, they're not using it. But we definitely encourage it, and we can help them with it and do everything we can to get them to use one. But the small systems especially, that's not their priority. They're gonna get in there and do what they want to do and not read an SOP or utilize that. But we certainly hope they would.
All right, well, let me wrap up here. We're coming up against 2:30. We need to break. A couple things I want to, well, several things I want to point out. First, to thank the panelists for these great presentations and the panel discussion. A lot of good information, a lot more work to be done on DBPs. So, and if you look at the questions, there was Allison Dugan from EPA dropped in a link to the status of the supplies for the hydrant samplers if you want to get that. If you have any more questions for the panelists, they all have their contact information as part of their slides. The slides are available in the handout. And then again, just everyone take an hour break here and get ready for the sessions that start up at 3:30. So thanks, everybody.
Thank you.
Bye, thank you.